What does it actually mean to build a tiny piece of the universe inside a computer? Not a simulation in the video game sense. Not a swirling animation of stars and dust rendered for a screen, but something closer to real physics. The kind of physics a theorist studying quantum gravity might sketch out on a chalkboard, translated into a working circuit and run on a machine chilled down to a tiny fraction of a degree above absolute zero. That is roughly what a team of physicists said they had done in the winter of 2022. The machine involved was Google's Sycamore processor, sitting in a laboratory in Santa Barbara, California. It was the same chip Google had used a few years earlier for its widely reported claim of quantum supremacy. The idea that a quantum computer had, for the first time, solved a problem faster than any classical computer realistically could. Sycamore contains 53 superconducting quantum bits in total. For this particular experiment, only 9 of them were actually doing the work. 9 qubits, and a circuit built from 164 2-qubit logic gates. By the standards of modern computing, that is an almost absurdly small amount of hardware. A basic pocket calculator has more computational machinery behind it in some ways. But the team behind the experiment was small, focused, and unusually senior for such a modest piece of hardware. The theoretical side of the collaboration was led by Daniel Jackson, a physicist at Harvard University who had spent years developing the theory that made the whole idea possible in the first place. Working alongside him were Maria Spirapule at the California Institute of Technology, Joseph Lycan at Fermilab, and Alexander Zlakapa, who was a graduate student at the Massachusetts Institute of Technology at the time. On the hardware side was Hartmut Neven, who runs Google's quantum computing research group. They had been building toward this moment for a while, and in January of 2022, they finally ran the experiment. Described in plain language, the procedure sounds strange. The team encoded a single qubit of quantum information into a cloud of entangled particles. Then they applied a carefully timed pulse that coupled the two halves of the system together. A kind of interaction designed to imitate something very specific from general relativity, negative energy, the theoretical ingredient that could, in principle, prop open a wormhole long enough for something to pass through it. Then they waited, and then they saw it. A sharp, distinct peak in the data. The qubit of information had vanished from one side of the system and reappeared on the other. In the language of quantum information science, that is teleportation, and by itself, it was not new. Physicists have been moving quantum information from one place to another inside a controlled system for years. This is a well-established technique, not a mysterious phenomenon. What made this particular result different was not the teleportation itself, but the interpretation the team placed on top of it. They were not claiming to have performed another routine teleportation experiment. They were claiming that what they had built and observed was a working, physical model of a traversable wormhole. In their description, the qubit had not simply been shuttled from one location to another inside a chip. It had, in a mathematical sense, fallen into a black hole on one side of a miniature holographic universe, passed through the throat of a wormhole connecting the two sides, and emerged from a second black hole on the other. On the 1st of December that year, the result appeared on the cover of the journal Nature, one of the most prestigious outlets in all of science. The New York Times covered it. So did The Guardian, New Scientist, and the physics publication Quantum magazine. Caltech's own press release described it as a first-of-its-kind quantum gravity experiment performed on a chip. For a few weeks, it genuinely looked as though physicists had found a way to drag one of the most abstract ideas in theoretical physics, quantum gravity, into an actual laboratory, onto an actual chip, running for a few seconds at a time, and then, Slowly, the cracks began to show. Other physicists, reading through the technical details of the paper rather than the headlines summarizing it, started asking a question that most of the popular coverage had skipped entirely. Yes, the 9 qubits had clearly done something. Nobody disputed that the experiment ran, or that the data came out looking a certain way. But what exactly had happened, and whether it had anything meaningful to do with gravity, was about to become one of the most closely watched and, at times, uncomfortable disputes in modern theoretical physics. To understand why that question was even askable, it helps to step back and talk about a strange but well-established idea in physics called holography. Some quantum systems, when you examine them the right way, behave exactly like gravitational systems existing in one additional dimension. Not approximately, not as a loose metaphor, exactly, in the sense that the mathematics describing the two systems can be shown to be interchangeable. Anything one description can do, the other description can do too. Term for term, physicists call this correspondence holography, and the idea has been part of serious theoretical physics since the 1990s. One way to picture it is to imagine a pair of unusual three-dimensional glasses. Take the glasses off, and you are looking at a quantum system, some particles interacting according to the ordinary rules of quantum mechanics. Nothing overtly gravitational about it. Put the glasses on, and the very same system now looks like curved space-time, complete with gravity, black holes, and, under the right conditions, wormholes. It is the same underlying physics, described in two completely different mathematical languages that happen to say exactly the same thing. This correspondence, sometimes called the holographic principle, or, in its most famous specific form, the anti-Darcy and conformal field theory correspondence, traces back to work by the physicist Juan Maldacena in 1990. Maldacena was trying to understand string theory, and in the process he found that a certain kind of quantum theory living on the boundary of a region of space was mathematically identical to a theory of gravity living inside that region. It was a strange and, at the time, startling result, because it suggested that gravity itself, usually treated as one of the 4 fundamental forces in its own right, might actually be a kind of emergent phenomenon, something that arises out of the collective behavior of quantum particles that have nothing obviously gravitational about them individually. The idea grew out of decades of earlier work on black hole thermodynamics, particularly a puzzle raised in the 1970s by Jacob Bekenstein and Stephen Hawking, who showed that black holes have entropy and temperature, behaving in some ways like ordinary thermodynamic objects even though they are made of curved spacetime rather than atoms. That black holes seem to store information the way an ordinary physical system does was one of the clues that eventually led toward holography, the quantum system used in the Sycamore experiment is one particular example of this kind of holographic duality, called the Sachdev-Ethkatav model, often referred to for short as the SYK model, named for the 3 physicists who developed it, Sabir Sachdev, Ginwu, and Alexei Katav. The model describes a collection of particles called Madrana fermions, all interacting with each other according to a specific random pattern of couplings. On its own, described this way, it sounds like a fairly abstract piece of condensed matter theory, the kind of model a physicist might use to study exotic materials. But the SYK model has a striking, almost surprising feature. Put the holographic glasses on, and this soup of randomly interacting fermions starts to look like a small, 2-dimensional universe containing gravity. Inside that toy universe, you can have black holes. In principle, you can have wormholes. What makes the SYK model such a valuable stand-in for a genuine gravitational system is a property related to chaos. In 2016, the physicists Juan Maldacena, Douglas Stanford, and Stephen Shenker demonstrated that every quantum system has a maximum possible rate at which information contained inside it can scramble. Effectively, a universal speed limit on how fast chaos can spread through a quantum system, set by the system's temperature and by Planck's constant, one of the fundamental constants of nature. Black holes, according to the mathematics, sit exactly at that speed limit. They are, in a very precise sense, the fastest scramblers of information that physics allows. The SYK model remarkably saturates the very same bound. This is not treated as a coincidence by physicists working in the field. It is considered a signature of the underlying gravitational duality. Systems that scramble information at the maximum allowed rate are, when viewed through the holographic lens, the same mathematical objects as black holes. The connection is not just an analogy or a loose resemblance. It is treated as a precise, testable mathematical identity. There was, however, a serious practical problem standing in the way of actually running this model on real hardware. The full version of the SYK model, the one that genuinely reproduces gravitational behavior in a convincing way, is enormous. To get the emergent gravity to show up clearly, you need a large number of interacting fermions, which translates mathematically into hundreds of interaction terms that all have to be accounted for simultaneously. No quantum computer that exists today, Sycamore included, can run a system that large. If the team wanted to actually perform this experiment in a real laboratory rather than only on paper, they needed a way to shrink the model down dramatically without destroying the very feature that made it interesting in the first place. Its gravitational behavior. That is where machine learning entered the picture. The team used a learning algorithm to prune the model down, systematically removing interaction terms one at a time, keeping only the ones that seemed to matter most, and allowing the algorithm to converge on a dramatically simplified version of the theory, which they called a sparsified SYK model. By the time the process finished, they were left with something small enough to actually run 7 fermions, a small handful of interaction terms, compact enough to fit onto 9 qubits. Crucially, the team argued that this stripped-down version remained faithful enough to the original theory that it still behaved gravitationally in the relevant sense. So, they went ahead and ran it. The mechanism that turns a simplified quantum system like this into something resembling a wormhole traces back to theoretical work Daniel Jafferis had done years earlier. In a 2016 paper written together with Ping Gao and Erin Wall, what they showed, working purely on paper, was that if you take two quantum systems that are already entangled with each other, and you couple them together in a very specific, carefully chosen way, then, on the gravitational side of the holographic dictionary, that coupling looks exactly like a pulse of negative energy. And negative energy, according to general relativity, is precisely the ingredient needed to prop a wormhole open. Left alone, a wormhole connecting to black holes pinches shut almost immediately, far too quickly for anything to cross through it. Introduce a carefully timed pulse of negative energy, though, and for a brief moment, the throat of the wormhole can stay open long enough for something to pass. This theoretical proposal connects to a broader and, at the time it was introduced, quite startling conjecture in theoretical physics known as ER equals EPR, put forward around 2013 by Juan Maldacena and Leonard Susskind. The idea, compressed into a slogan, is that entanglement between two quantum systems, the EPR part of the name, referring to a famous 1935 thought experiment by Einstein, Podolsky, and Rosen, might be physically the same thing as a wormhole connecting those two systems in spacetime, the ER part, referring to a 1935 paper on wormholes by Einstein and Nathan Rosen. If that conjecture is correct, then entanglement and geometry are, in some deep sense, the same underlying phenomenon viewed from different angles. The traversable wormhole protocol that Jafferis, Gao, and Wall developed was, in effect, an attempt to make that abstract correspondence concrete and, in principle, testable. This was a theoretical machinery the Sycamore team was trying to imitate experimentally. The carefully timed coupling pulse applied between the two halves of their 9-qubit system served as the experimental stand-in for the negative energy pulse from the theory, and when they applied it, the qubit of information moved through, appearing on the far side of the system. The team did not stop at claiming they had observed a single teleportation signal. They argued that they had identified 5 separate, specific signatures, each one supposedly a fingerprint of how a genuine traversable wormhole would be expected to behave. The first was scrambling and thermalization. As the qubit passed through the system, it scrambled and spread out the way information is expected to behave when it falls into a black hole, becoming smeared across many degrees of freedom rather than staying localized. The second was timing. The signal on the far side of the system appeared with a small delay relative to when it was sent. The kind of delay general relativity predicts for something, crossing a curved region of spacetime rather than moving instantaneously. The third was causal ordering. The various signals that made up the experiment came out in the correct sequence, consistent with a well-defined causal structure rather than random noise. The fourth, which the team treated as something close to a smoking gun, was a pattern in the data they called perfect size winding, a specific correlation structure that, according to the theory, should only appear if genuine gravitational dynamics were at play. And the fifth was that the coupling between the two halves of the system behaved, quantitatively, the way a negative energy shockwave was predicted to behave in the underlying theory, 5 fingerprints, all supposedly pointing toward gravity. If the team's interpretation held up, this would have been the first time in the history of physics that a controlled laboratory experiment had reproduced a genuine piece of gravitational physics, not by building an actual black hole, which nobody was claiming to have done, but because the quantum system on the chip was supposed to be mathematically identical to a black hole and wormhole system, simply viewed through the other side of the holographic glasses. That was the claim, and the question that a group of physicists at the University of California, Berkeley, began asking almost immediately afterward was a simple one on the surface. Were the glasses really on? In other words, was the small system on the chip actually dual to a gravitational description in the rigorous sense the theory demanded? Or did it merely resemble one in certain superficial respects? On the 15th of February, 2023, roughly 2.5 months after the Nature paper's publication, 3 physicists at Berkeley uploaded a paper to the online physics archive that, by most accounts, nobody at Caltech, Harvard, or Google was especially eager to read. Their names were Bryce Cobrin, Thomas Schuster, and Norman Yao. They were not outsiders to this corner of physics. Yao runs a research group at Berkeley, working on precisely the overlap between quantum information theory and gravitational physics, the same territory the Sycamore experiment had been built on. When the Nature paper came out, Yao and his students did what any careful research group in this position tends to do. They sat down and worked through the mathematics, trying to understand exactly how a system as small as 9 qubits could be doing everything the headlines claimed it was doing. What they found was a significant problem: the sparsified Hamiltonian. meaning the mathematical description of the stripped-down version of the SYK model that the machine learning algorithm had produced, had a specific and, for this purpose, damaging mathematical property. It was what physicists call fully commuting. Understanding exactly what that technical term means is not necessary to understand why it mattered, but a picture helps. Imagine a real gravitational system, something like a black hole, as a room full of people in the middle of a panic. Everyone is shouting over everyone else, bumping into one another, and within a few seconds the whole scene has become genuinely chaotic. If you tried afterward to reconstruct exactly who said what and in what order, you could not do it, because the information has been smeared and scrambled across the entire room. That, roughly, is what physicists mean when they describe a quantum system as scrambling and thermalizing, and it is exactly the kind of behavior gravity is expected to produce at the quantum level. A fully commuting system is not like that room at all. It is closer to a room full of people who have all quietly agreed, in advance, to completely ignore each other. They can be in the same room together. They can even be performing actions at exactly the same moment. But nothing any one of them does interferes with, or depends on, what anyone else is doing. Each person simply carries out an assigned, independent action in parallel with all the others. That, in essence, was the kind of system the sparsified experiment had actually built. And that distinction, subtle as it sounds when described this way, turned out to create three separate, serious problems for the original interpretation, one after another. The first problem concerned thermalization. The original team had listed scrambling and thermalization as one of their 5 gravitational fingerprints. But a fully commuting Hamiltonian, by its very mathematical nature, cannot thermalize. It is structurally incapable of it, because its individual pieces simply do not interact with each other in the chaotic, cross-talking way that would be required for real thermalization to occur. So that first fingerprint, the Berkeley group argued, was never actually present in the experiment. It had only appeared to be present. The second problem concerned the supposed smoking gun. The pattern the original team had called perfect size winding, which they had presented as the clearest available signature of a genuine gravitational interpretation. Kobrin, Schuster, and Yau showed that this exact pattern is something small. Fully commuting quantum systems produce routinely, as a simple consequence of their mathematical structure, entirely independent of whether any gravitational physics is involved at all. In other words, the single piece of data the original team had leaned on most heavily to lock in the wormhole interpretation turned out to be, essentially, an artifact of the simplification process itself, rather than genuine evidence of anything gravitational. This kind of mistake has a name among physicists, sometimes called the lamppost problem, after the old joke about a man searching for his lost keys under a street lamp. Not because that is where he dropped them, but because that is where the light happens to be. In this case, it is a subtler version of that joke, finding a pattern precisely in the place you happen to be looking, not because the pattern carries any deep physical meaning, but because the very simplification that made the pattern visible in the first place was also the thing that generated it. The third problem concerned the teleportation signal itself. The core result, everyone agreed, was real in some sense. When the Berkeley group examined closely how the signal actually behaved in detail, its shape and timing did not match what would be expected from a qubit genuinely crossing a traversable wormhole according to the theory. The dynamics were off. The match between the experimental data and the theoretical prediction was considerably looser than the original paper had suggested. Taken together, 3 of the original 5 supposed fingerprints were now either entirely absent or badly compromised. The reaction within the physics community was measured, but unmistakable. John Preskill, a theoretical physicist at Caltech, who had not been part of either research group, told the publication Quanta magazine that he felt the evidence for a gravitational interpretation of the experiment was weakening. Vijay Balasubramanian, a physicist at the University of Pennsylvania who works in this exact area, and other researchers close to the debate, including Vincent Su at Berkeley, framed the question hanging over the entire episode in blunt terms: was quantum gravity in the laboratory, as a research program, effectively dead? It was a sharp way to put it, and at the time, nobody had a clean, agreed-upon answer. The original team did not simply concede the point. Jafferis and his collaborators published a response arguing that even a fully commuting Hamiltonian could still capture something scientifically meaningful, even if it fell short of representing a complete, rigorous gravitational duel. Ping Gao, one of Jafferis's longtime collaborators at Harvard, went further and proposed, in a separate paper, that what the experiment had actually simulated might best be described as a kind of pseudo-holographic behavior, not full-fledged gravity in the strict technical sense, but not nothing either, something occupying a middle ground, with its own teleportation mechanism operating under a different parameter regime than a genuinely traversable wormhole would require. This entire dispute traces along a fault line that runs through the whole holography research program more broadly. The difference between a quantum system that is dual to a gravitational description exactly, in the full mathematical sense, interchangeable term for term, and a system that merely mimics some of gravity's outward behavior under specific, limited conditions. The former is, in effect, a precision scientific instrument. The latter is closer to a suggestive analogy, useful for intuition, but not something you can lean on for rigorous conclusions. As of early 2026, the Sycamore wormhole experiment appears to sit somewhere between those two categories, and the field, as a whole, has not reached agreement on exactly where along that spectrum it belongs. For roughly 2 years, this dispute sat mostly in the informal, non-peer-reviewed physics archive literature, debated in papers, conference talks, and quiet conversations among specialists, without any formal resolution. Then, in July of 2025, the journal Nature did something it does, comparatively rarely. It published the Berkeley critique formally, as a peer-reviewed Matters Arising article. The journal's mechanism for publishing serious scientific objections to previously published work, alongside a formal reply from the Jafferis team. The original 2022 paper has not been retracted. It remains part of the scientific literature, but it now carries, attached to it permanently, a formal, peer-reviewed statement from another group of physicists, concluding that 2 of the 5 originally claimed gravitational fingerprints were not actually present in the data, and that a third was, in effect, an artifact produced by the very simplification process used to make the experiment runnable in the first place. The Jafferis team's formal reply, in essence, agreed that many of the physical processes their experiment ran on the learned, simplified Hamiltonian did not have a genuine gravitational description after all, while continuing to maintain that some of the processes still did. So where does that leave the original headline claim? The qubit was teleported from one side of the system to the other. That part is not in dispute. The experiment ran, and the data is the data. But whether what happened on those 9 qubits had anything meaningfully to do with gravity, in the way the original headlines suggested it did, remains an open question, one now carrying serious, formally documented doubt. Perhaps the most honest summary anyone in the field is willing to offer, as of 2026, is that the experiment showed something genuinely interesting. Whether that something amounted to a wormhole, or was instead an unusually clever, and in hindsight somewhat misleading, toy model, is simply not yet settled. And while the wormhole story was still working its way through this slow, public process of scientific correction, a different research group was already running a much larger experiment on an entirely different kind of quantum machine, aimed at a very different piece of physics altogether. This second experiment was not about a hypothetical wormhole connecting to toy black holes in an artificial universe carved out of 9 qubits. It was, in a strange and much more direct sense, about the actual universe we live in. 5,564 qubits. That is the number worth holding on to for this part of the story. The wormhole experiment used 9. This one used 5,564. The two machines are not the same kind of quantum computer, and the two teams were not attempting to do the same kind of thing at all. But the sheer contrast in scale is worth noticing before anything else. Whatever this second experiment was actually accomplishing, it was doing it on a machine more than 600 times larger than the one behind the wormhole story. The paper describing this second experiment appeared in the journal Nature Physics on the 4th of February, 20. The team behind it was led by Zlatko Papik at the University of Leeds, along with researchers at the Jülich Supercomputing Center in Germany, and Geneviève de Source at the Institute of Science and Technology, Austria. The hardware they used was a D-Wave quantum envelope, a fundamentally different kind of quantum machine from Sycamore's gate-based architecture, integrated into a larger classical supercomputing system at the Jülich Center. Different hardware and an entirely different physics question. What were they actually simulating? In a sense, they were probing the end of the universe, or at least one possible version of how that end might unfold. The underlying idea traces back to work done by the physicist Sidney Coleman in the late 1970s. Here is the basic picture. The universe we live in might not actually be sitting in its true, lowest possible energy state. It might look stable. It might feel completely stable in every practical sense. But underneath that apparent stability, it might be resting in a kind of valley that is not the deepest valley physically available to it. There could exist, somewhere in the abstract landscape of possible physical configurations, an even lower valley, a more stable arrangement of the fundamental laws of physics that our universe simply has not found its way into yet. Physicists refer to the valley we appear to currently occupy as a false vacuum, and the theoretically deeper, more stable valley as the true vacuum. If that basic picture is correct, then at some point, somewhere, the universe could find its way down into that deeper valley, not gradually and not gently, but through a genuinely quantum mechanical process called tunneling. A small region of space, somewhere out in the cosmos, would spontaneously flip from the false vacuum configuration into the true vacuum configuration, forming what physicists call a bubble. Once such a bubble formed, it would begin expanding outward at the speed of light. Inside that expanding bubble, the fundamental laws of physics would be different from the laws operating outside it. The fundamental constants of nature would take on different values. Atoms, as we know them, might no longer hold together at all. Chemistry, in any form remotely familiar to us, would simply cease to function. And because the bubble's edge would be moving at the speed of light, nobody on the wrong side of it would ever see it coming. The light announcing its arrival would reach you at precisely the same instant the bubble itself did. This is not a fringe idea confined to speculative corners of theoretical physics. Measurements of the mass of the Higgs boson at the Large Hadron Collider, combined with independent measurements of the mass of the top quark, place what physicists call the electroweak vacuum of the standard model of particle physics into a region often described as metastable, not definitively stable in the way a true vacuum would be, and not definitively unstable either, but sitting uncomfortably close to the dividing line between the two. Coleman's original calculations suggested that the amount of time it might take for our universe to eventually tunnel down into a true vacuum state was, very roughly, comparable to the current age of the universe itself, which is a fairly unsettling way of saying that we probably have a very long time before anything like this happens, or possibly do not, since the estimate carries enormous uncertainty. Nobody actually knows the real timescale with any confidence, what nobody had ever managed to do, until this experiment was actually watch this fundamental mechanism play out directly, even in a small, simplified model system, even at a tiny scale, far removed from cosmological reality. That is precisely what the Leeds, Jülich, and Institute of Science and Technology, Austria collaboration set out to build. They arranged 5,564 superconducting flux qubits into a circular pattern and configured the whole system as what physicists call a quantum Ising model, a well-understood theoretical framework that functions almost like a physics toolkit, capable of imitating the behavior of many different kinds of physical systems depending on how it is tuned. In this particular case, the team tuned their qubit array so that the entire setup behaved, effectively, like a one-dimensional slice of a false vacuum. Then they triggered the transition, and they watched what happened. Small, quantized bubbles of true vacuum began forming inside the array almost immediately. Small ones appeared first, and then progressively larger ones followed. Some of these bubbles, by the time they had fully grown, involved the equivalent of 300 individual spin flips, meaning 300 qubits changing their state together in a coherent, correlated pattern. The bubbles expanded outward. They encountered one another. They collided and interacted, exactly the kind of dynamical behavior the underlying theory predicted. And the research team could observe all of this playing out in real time, directly in the data coming off the quantum annealer, the entire process held together in a coherent, trackable way for more than a microsecond. On the scale of everyday human experience, a microsecond sounds impossibly brief, essentially nothing. But for a quantum system operating at this scale, it represents more than 1,000 of the system's own intrinsic time units, an enormous stretch by the standards of quantum coherence. It was long enough to study the underlying dynamics seriously, long enough to write down mathematical equations describing precisely how the bubbles formed and grew, and long enough to compare the experimental results directly against theoretical predictions. There is, however, an important caveat attached to this result. The experiment was carried out in one spatial dimension. The actual universe we live in is, as far as physicists can tell, three-dimensional. So what the team observed is not a literal, direct preview of exactly how false vacuum decay would unfold in our real three-dimensional cosmos. It is better described as a faithful, well-controlled simulation of how the underlying mechanism behaves in a deliberately simplified, lower-dimensional version of the problem. The team's own paper explicitly notes that three-dimensional versions of the same experiment are, in principle, achievable on similar hardware, given further development, and that is generally understood to be the direction the field is now heading. What is particularly notable about this second experiment, in contrast to the wormhole story, is that essentially nobody has challenged it in the way the wormhole experiment was challenged. The underlying physics is considerably more conventional. The quantum Ising model is extremely well understood theoretically, studied for decades in the context of condensed matter physics, long before anyone thought to apply it to cosmology. The qubits, according to independent analysis, behaved exactly the way the governing equations predicted they should. There has been no equivalent of the Berkeley critique directed at this result, at least not so far. But underneath both of these stories, the celebrated and later disputed wormhole experiment, and the quieter, largely unchallenged false vacuum experiment, sits a shared and much quieter problem, one that applies to both cases even though one experiment turned out to be contested and the other has not been. It is the problem the wormhole controversy dragged fully into the open, forcing the field to confront it directly instead of leaving it as a background technical concern. How, exactly, do you know when a quantum simulation is actually showing you the truth about nature, rather than merely showing you an artifact of the specific hardware and specific simplifications you happen to use? For most of the history of modern physics, there has been a fairly simple, reliable rule for telling a genuine result apart from a mistaken one. You ran an experiment, then someone else, in a different laboratory, with independently built equipment, ran the same experiment again. If the two groups arrived at the same answer, the result was probably real. If they did not, then somebody, somewhere, had made an error, and the field went looking for exactly where that error had crept in. This rule still works for the overwhelming majority of what physicists do. It works for particle accelerators. It works for telescopes and astronomical observations. It works for chemistry, for materials science, and for nearly any field where building a second, independent copy of the apparatus and trying again is a realistic option. That rule is starting to break down, specifically for quantum simulation. And the reason is not a flaw in the method so much as a direct consequence of what quantum simulation is for. The entire point of running a piece of physics on a quantum computer, rather than an ordinary classical one, is to do something a regular computer genuinely cannot do. If an ordinary laptop could simulate the full SYK model with, say, 100 fermions, or could simulate false vacuum decay across a system of 5,000 interacting qubits, nobody would need a quantum machine in the first place. You would simply run the calculation on conventional hardware and be done with it. A quantum computer earns its scientific value precisely in the regime where classical computers cannot keep up. But that creates a genuinely strange situation. If your quantum simulation tells you something surprising, something new about how a wormhole behaves, or about how the universe might eventually collapse into a deeper, more stable vacuum state, how exactly are you supposed to check whether that answer is correct? You cannot simply run the same calculation on a classical computer for comparison, because if you could do that, you would not have needed the quantum machine to begin with. That, in a nutshell, is the verification problem. It is a quiet, largely technical issue that has been sitting in the background of quantum computing research for years. And the wormhole controversy is what finally dragged it into the spotlight for a much wider audience at its core. This connects to a genuinely fundamental question in quantum computing theory. Quantum computers are believed, and in some specific, mathematically proven cases known, to be able to solve certain classes of problems far more efficiently than any classical computer possibly could. However, verifying that a quantum computer has actually produced the correct answer to one of these problems is often just as computationally difficult as solving the problem classically would have been in the first place. In other words, the exact same property that makes quantum simulation scientifically powerful, its ability to outrun classical computation, is also precisely what makes its outputs so difficult to independently confirm. There are tools available that help address parts of this problem. Techniques such as cross-entropy, benchmarking, shadow tomography, and randomized benchmarking can each check specific, limited aspects of how well a given quantum device is performing. catching certain categories of hardware error, or verifying certain statistical properties of the output. But none of these tools, individually or combined, currently provides a fully general, fully reliable way to certify that an arbitrary quantum simulation is producing physically correct results. They are useful diagnostic instruments, not a complete solution. It is worth pausing to consider what the Berkeley Group actually did when they investigated the wormhole experiment, because it illustrates the current limits of verification quite clearly. They did not rerun the original experiment. They did not build their own competing version of the wormhole apparatus on separate hardware. Instead, they took the underlying mathematics the original team had used, examined it closely and carefully, and discovered that the model was not actually doing what the original team believed it was doing. The check, in the end, was not experimental at all. It was purely theoretical. 3 physicists, working with pencil, paper, and careful mathematical reasoning, worked through the full consequences of the systems governing Hamiltonian and discovered that 2 of the 5 claimed gravitational fingerprints were simply not present, and that the third was an artifact produced by the very process used to shrink the model down to a runnable size. This is, in a sense, exactly the kind of correction the scientific community used to handle quietly, inside the ordinary peer review process, before a paper was ever published in the first place. In this particular case, it happened publicly, in the full view of the scientific community and eventually the wider public. Roughly 2 years after the original paper had already appeared on the cover of one of the most prominent journals in all of science. The field, in other words, had moved considerably faster than its own internal checking process could keep up with. This is not an isolated pattern confined to superconducting qubit experiments. In late 2025, a research team at Swinburne University of Technology in Australia, led by Alexander Delios, reported a new technique specifically designed for validating the outputs of a different kind of quantum machine, known as a Gaussian boson sampling device, a specialized type of photonic quantum computer built to perform one particular, highly specific calculation extremely efficiently. When Delios and his colleagues applied their newly developed validation method to a previous landmark experiment in that particular area of quantum computing, one that had been celebrated at the time as a genuine milestone, they found errors, real, previously unnoticed errors, in a result that the field had already accepted and moved past. The Swinburne result does not directly say anything about the wormhole experiment or about the false vacuum decay simulation. It involves an entirely different machine built around an entirely different physical problem, but it points toward exactly the same underlying nerve running through the whole field. Quantum computers are now routinely doing things that cannot be independently checked using classical methods, and whenever researchers do eventually develop the tools needed to check them properly after the fact, they keep discovering that the real picture is considerably messier than the original headlines suggested. There is something structurally familiar about this overall pattern. If you look slightly outside physics, it closely echoes the early history of computational simulation in several other scientific fields, including climate modeling, protein folding research, and economic forecasting, in each of which the underlying computational tools advanced considerably faster than the methods available for properly validating them. In those fields, it took years of careful, sometimes uncomfortable work to clearly distinguish between a model that produced an output and a model that had actually told researchers something true about the real world. The current era of quantum simulation may simply be going through its own version of that same reckoning. On its own accelerated timeline, there is, fortunately, a plausible path through this particular uncertainty. Researchers generally describe the way forward as involving tighter integration between machine-learned simplification techniques of the kind used to shrink the SYK model down for the wormhole experiment, and methods that come with provable mathematical fidelity guarantees, so that researchers know in advance exactly how much a given simplification is allowed to distort the underlying physics. Alongside this, the field is pushing toward larger-scale quantum annealers and gate-based devices operated specifically in regimes where multiple independent forms of verification, including comparisons against known classical limits, comparisons against alternative dual theoretical descriptions, and arguments based on underlying symmetries of the system, can all be applied simultaneously to cross-check a single result. A broader cultural shift within the field is also widely seen as necessary, one that places greater emphasis on publishing not only the striking, headline-worthy outputs of an experiment, but the full diagnostic history, sometimes called the pedigree, of the underlying model used to produce it, exactly how it was simplified, exactly what was thrown away in the process, and exactly what independent checks were performed before publication. Taken together, these two experiments demonstrate something considerably subtler than the dramatic framing that surrounded them in the popular press, subtler than headlines about wormholes appearing on a chip or vacuum bubbles forming inside a ring of superconducting circuits. What they actually show is that the long hypothesized convergence between quantum information theory and gravitational physics is no longer a purely theoretical conversation confined to chalkboards and physics archive papers. It is becoming experimental. It is becoming messy. It is becoming genuinely contested in places. And, precisely because of all of that, it is becoming real, in the sense that real science tends to look. The signal produced by 9 qubits back in 2022 was never going to single-handedly settle the fundamental nature of spacetime, and the next several thousand qubits of quantum annealer hardware are not going to definitively pronounce on the long-term stability of the universe either. Yet each individual experiment, however small, however contested, incrementally enlarges the domain of physics in which gravity and quantum mechanics are forced to answer to the exact same cold, hard experimental data in that slow, sometimes uncomfortable process of enlargement lies what might be called a quiet revolution happening within theoretical physics right now. Researchers are, in effect, learning to listen with new instruments, fully aware that some portion of what those instruments pick up will turn out to be echo, artifacts of simplification and hardware limitation rather than genuine signal, and that some portion will turn out to be real physical signal after all, with the field only gradually, through hard-won, rigorous checking, becoming better able to tell the two apart. None of this means the broader field of quantum gravity research is somehow broken or in crisis. Holography, as a theoretical idea, remains an extraordinarily powerful and well-supported framework within theoretical physics. The SYK model remains a genuinely useful theoretical tool, regardless of the controversy surrounding one particular hardware implementation of it. Most theoretical physicists working in quantum gravity continue to believe that the holographic principle, in some form, is very likely correct. The false vacuum decay simulation performed at Jülich is regarded as solid, careful work. The bubbles really formed, the dynamics really matched the underlying theory, and the eventual path toward a fully three-dimensional version of the experiment is real. With researchers actively working toward it, what has genuinely changed? In the aftermath of all of this is what physicists are now willing to claim out loud. and how carefully they are willing to phrase those claims. The Sycamore wormhole experiment did not simply teach the field a narrow lesson about one particular simplified Hamiltonian running on one particular chip. It taught a much broader lesson about how researchers ought to talk about quantum simulation results in general. A teleportation signal is not automatically a wormhole, even if the underlying mathematics can, under certain interpretations, be read as suggesting it might be one. A pattern appearing in experimental data is not automatically a fingerprint of gravity, simply because a research team has chosen to call it one. A 9-qubit experiment running for a few seconds on a chip in Santa Barbara is not, by itself, confirmation that space-time fundamentally emerges from quantum information. However much a great many theorists might want that particular idea to turn out to be true, the deeper questions underlying all of this remain genuinely, entirely open. Physicists do not currently know whether the space-time we actually inhabit is fundamentally holographic in the way the underlying mathematics sometimes seems to suggest. They do not know whether our universe is currently sitting inside a false vacuum, quietly waiting on some unknown timescale for a bubble of true vacuum to nucleate somewhere out in the dark and unravel everything we know. And they do not yet know whether the next generation of quantum simulations, running on ever larger and more capable hardware, will finally deliver genuine, trustworthy answers to questions like these, or whether those simulations will simply keep producing more sophisticated artifacts dressed up, at least initially, as genuine discoveries. What is known, with complete certainty, is that somewhere in Santa Barbara, a dilution refrigerator continues, humming quietly with 9 qubits inside it. Somewhere in Jülich, a very different refrigerator hums, along with 5,564 qubits inside it. In both places, physicists are doing something genuinely unprecedented, using quantum systems to ask the universe questions that have simply never been posed inside a laboratory before. Sometimes the answers that come back are real. Sometimes they are artifacts. And right now, honestly, researchers are not always immediately sure which is which. It is worth stepping back even further, because this entire episode sits inside a much longer story about the relationship between computation and physics, one that stretches back decades before anyone had ever heard of a qubit. The physicist Richard Feynman is often credited with originating the modern idea of quantum simulation in the first place. In a lecture he gave in 1981, where he pointed out that if you wanted to accurately simulate quantum mechanical systems, ordinary classical computers would always struggle, because the resources required grow exponentially with the size of the system you are trying to simulate. His proposed solution, at the time almost entirely theoretical, was that you would eventually need computers that were themselves built out of quantum mechanical components, machines that could exploit superposition and entanglement directly rather than trying to laboriously calculate their consequences one classical bit at a time. 4 decades later, experiments like the Sycamore wormhole simulation and the Jülich false vacuum experiment represent an early, still quite limited, but genuinely real realization of exactly the vision Feynman first sketched out. The broader landscape of quantum hardware has diversified considerably since those early theoretical proposals. Gate-based superconducting processors, like Google's Sycamore chip and comparable machines built by IBM, manipulate individual qubits through precisely controlled microwave pulses, applying sequences of logical operations similar in spirit, though not in underlying physics, to how a classical computer processor executes instructions. Quantum annealers, such as the D-wave machine used in the Jülich false vacuum experiment, work rather differently. Instead of executing a discrete sequence of logical gates, They are designed to naturally settle into the lowest energy configuration of a carefully engineered physical system, a property that makes them particularly well suited to certain kinds of optimization problems and, as it turns out, to simulating physical systems like the Ising model used to represent false vacuum decay. Photonic quantum computers, like the Gaussian boson sampling device studied by the Swinburne University team, take yet another approach entirely, encoding and manipulating quantum information using individual particles of light rather than superconducting circuits at all. Each of these architectures has its own particular strengths, its own particular sources of error, and, as the past few years have made increasingly clear, its own particular challenges when it comes to verifying that its outputs can actually be trusted. Error correction remains one of the central unsolved engineering challenges across all of these hardware platforms. Individual qubits, regardless of which physical technology is used to build them, are extraordinarily fragile, prone to losing their delicate quantum states through a process called decoherence, caused by even the faintest unwanted interaction with their surrounding environment. Whether that is stray electromagnetic radiation, tiny vibrations, or simply residual heat that the dilution refrigerator has not managed to remove. Building quantum computers that can reliably correct for these errors, without the correction process itself introducing more noise than it removes, has been one of the central technical hurdles of the entire field for decades, and continues to be an area of intense, active research. The 9-qubit wormhole experiment and the 5-1000-5-60-4-QUBIT false vacuum experiment were both, in their own ways, examples of researchers working carefully within the practical limitations imposed by present-day, imperfect, not yet fully error-corrected quantum hardware, which is itself part of why questions about verification and trust have become so pressing across the field as a whole. This same overlap between quantum information, theory, and gravitational physics, the theoretical territory that made the Sycamore wormhole experiment conceivable in the first place, also underlies one of the more celebrated theoretical achievements in this area of physics over the past several years. A set of calculations, carried out entirely on paper, addressing what is known as the black hole information paradox. The paradox, first raised by Stephen Hawking in the 1970s, concerns what ultimately happens to information that falls into a black hole. According to Hawking's own calculations at the time, black holes should slowly evaporate over enormous timescales by emitting a faint form of radiation, now called Hawking radiation, and that radiation appeared, according to his original analysis, to be completely random, carrying no trace whatsoever of whatever information had originally fallen into the black hole. This directly conflicts with a foundational principle of quantum mechanics, which holds that information can never truly be destroyed, only ever scrambled or hidden, never fully erased from the universe. In 2019 and 2020, several independent groups of theoretical physicists, including researchers building directly on the same holographic framework underlying the SYK model and the wormhole experiment, showed, using a mathematical technique involving what are called replica wormholes, that Hawking's original calculation had been missing an essential ingredient. When that ingredient is properly included, the radiation emitted by an evaporating black hole does, in fact, gradually come to encode the information that fell in, consistent with the demands of quantum mechanics after all, following a specific mathematical curve called the Page curve. That had been predicted on more general grounds decades earlier by the physicist Don Page. This result, achieved entirely through theoretical calculation rather than any physical experiment, is widely regarded within the field as one of the strongest pieces of evidence yet that the holographic correspondence between quantum systems and gravity is not merely a mathematical curiosity, but reflects something genuinely true about how our universe actually works. It is part of the same broader intellectual backdrop that made an experiment like the Sycamore wormhole simulation seem, to its original team, like a natural and exciting next step to attempt. It is worth spending a little time on the Sycamore chip itself, since the same piece of hardware carries its own earlier, related controversy that helps explain why so many physicists were primed to scrutinize the wormhole result so carefully when it appeared. Back in 2019, Google published a paper, also in Nature, claiming that Sycamore had achieved what researchers call quantum supremacy or quantum advantage, meaning that it had completed a specific, carefully chosen computational task in about 200 seconds. A task that the Google team estimated would take the largest classical supercomputer in the world roughly 10,000 years to complete using the best available classical algorithms at the time. The claim was immediately contested. IBM, a competitor in the field of quantum hardware, argued fairly quickly that with a more cleverly optimized classical algorithm and enough available storage, the same calculation could actually be completed on a classical supercomputer in a matter of days rather than millennia, which, if correct, would dramatically narrow the claimed advantage without eliminating it entirely. Over the following few years, the picture continued to shift. In 2021 and again in 2022, separate groups of researchers, including a team led by Feng Pan and Pan Zhong, published improved classical simulation methods that managed to reproduce the output of Google's original 2019 supremacy experiment on ordinary classical hardware in a matter of hours, and in some later refinements, considerably less. This did not mean that quantum computers were suddenly useless, or that Sycamore's underlying hardware performance had been misrepresented. It meant, instead, that the specific claim of an essentially unbeatable classical time cost had been a moving target, gradually eroded by classical, algorithmic improvements that nobody had anticipated at the time of the original announcement. This history is directly relevant to understanding the wormhole controversy, because it illustrates a pattern that recurs constantly throughout the short history of quantum computing so far. An initial, dramatic claim, followed by a slower, more careful process of independent scrutiny that often ends up walking the claim back, at least partially, without necessarily discrediting the underlying research entirely. This same historical backdrop is part of why the physicist John Preskill, the same researcher quoted earlier expressing doubts about the wormhole experiment's gravitational interpretation, is closely associated with a term that has become standard shorthand across the whole field, the noisy intermediate-scale quantum era, often abbreviated informally to describe roughly where quantum computing currently stands. Preskill introduced this framing in a paper in 2018, describing a period in which quantum computers have grown large enough, in terms of qubit count, to attempt genuinely interesting calculations that classical computers cannot easily reproduce, but remain far too small and far too error-prone to run the kind of large-scale, fully error-corrected quantum algorithms that would eventually deliver guaranteed, unambiguous quantum advantages across a wide range of practical problems. Both the wormhole experiment and the false vacuum decay experiment sit squarely within this noisy intermediate scale period, which is itself a large part of why questions about verification, artifacts, and trust have become so central to how the field now evaluates its own results. There is a deeper theoretical thread connecting holography, the mathematical framework underlying the wormhole experiment, to an entirely different and highly active area of modern theoretical physics, the study of quantum error-correcting codes. Around 2015, a group of physicists, including Ahmed Almhiri, Shidong, and Daniel Harlow, showed that the mathematical structure of holographic dualities closely resembles the structure of quantum error-correcting codes, the same general mathematical framework engineers use to protect fragile quantum information from noise and decoherence in actual quantum computer hardware. In this picture, information about the interior of a gravitational spacetime is not stored in any single localized place on the boundary quantum system, but is instead spread out and redundantly encoded across the whole boundary theory. In much the same way a good error-correcting code spreads a single logical qubit of information redundantly across many physical qubits, so that the loss of any small piece does not destroy the information as a whole. This connection has become one of the more actively pursued directions in theoretical quantum gravity research over the past decade, sometimes described using the language of tensor networks. Mathematical structures originally developed to efficiently describe large, complicated quantum systems in condensed matter physics, which turn out to provide a surprisingly natural geometric picture of how a holographic bulk spacetime can be built up, piece by piece, out of an underlying quantum system living only on its boundary. The SYK model itself, independent of its later use in the Sycamore wormhole experiment, has had a long and genuinely productive life within condensed matter physics, an entirely separate branch of physics concerned with the behavior of ordinary materials rather than with quantum gravity at all. Physicists studying so-called strange metals, unusual materials, including certain high-temperature, whose electrical resistance behaves in ways that standard theories of metals cannot easily explain, have found that variants of the SYK model provide one of the more promising theoretical frameworks for understanding this behavior. This is worth mentioning because it highlights something easy to lose sight of amid all the controversy over wormholes. The SYK model was never invented merely as a stepping stone towards simulating gravity on a chip. It has substantial, independent scientific value in a completely different area of physics, which is part of why the broader theoretical framework has retained credibility even as one particular, high-profile application of it came under serious scrutiny. It is also worth spending a moment on D-Wave Systems, the company that built the quantum annealer used in the false vacuum decay experiment. Since quantum annealing itself has had a somewhat contested history within the broader quantum computing community, D-Wave, a Canadian company, began selling commercial quantum annealing hardware considerably earlier than any other company was selling gate-based quantum processors. And for years afterward, there was genuine, sometimes heated debate within the physics community over whether D-Wave's machines were exploiting authentic quantum mechanical effects, including genuine entanglement and quantum tunneling, or whether their performance could be adequately explained using purely classical physics running underneath the hood. Over time, as D-Wave's hardware scaled up, and as more careful independent studies were conducted, a broad consensus emerged that D-Wave's annealers do exploit genuine quantum effects, including measurable entanglement among their qubits. Even though annealing hardware works according to fundamentally different principles than gate-based machines like Sycamore, and remains suited to a different, more specialized range of computational problems. The false vacuum decay experiment represents one of the more scientifically striking applications yet demonstrated for this particular style of quantum hardware, precisely because the Ising model that underlies the experiment maps naturally onto the kind of energy problems that annealers are specifically built to solve. Returning to the theoretical foundations for a moment, one of the more elegant pieces of the Holography story concerns how physicists actually calculate geometric properties of the gravitational side of the correspondence using nothing but quantum information sitting on the boundary theory. In 2006, the physicists Shinsei Ryu and Tadashi Takayanagi proposed a remarkably simple formula connecting entanglement, entropy, a purely quantum information theoretic quantity measuring how much one part of a quantum system is entangled with another, to the physical area of a particular kind of surface inside the corresponding gravitational spacetime. In effect, their formula says that the amount of quantum entanglement in the boundary theory directly determines the geometry, the actual curved shape of space on the gravitational side of the duality. This was a striking result at the time, because it suggested that the fabric of spacetime itself, ordinarily thought of as the most basic, fundamental stage on which physics plays out, might actually be built up out of quantum entanglement, rather than the other way around. It is one of the central pieces of evidence supporting the idea, sometimes summarized with the phrase "it from qubit," borrowed from an older phrase coined by the physicist John Wheeler. That information, in a deep sense, might be more fundamental to physical reality than space and time themselves. This idea, that space-time might emerge from entanglement, is part of what made the ER equals EPR conjecture, and by extension the whole traversable wormhole proposal that Gao and Wall developed, feel like such a natural next step for theorists to pursue. If entanglement really does build geometry, then two entangled quantum systems really might be connected by something functioning like a wormhole, a literal geometric bridge through space, rather than merely resembling one in some loose metaphorical sense. Testing that idea directly, even in the smallest, most simplified possible laboratory version, was always going to be an enormously difficult experimental undertaking, given how deep and abstract the underlying theoretical claims are. That difficulty is itself part of why the initial excitement around the 2022 Sycamore result was so intense, and also part of why the subsequent, more careful scrutiny turned out to matter so much once it arrived. It is easy, amid all of this abstract theory, to lose sight of the fact that quantum simulation as a broader technique has plenty of applications considerably closer to home than wormholes and vacuum decay. Applications where the verification problem, while still present, tends to be somewhat more tractable because the results can often be cross-checked against known experimental data from chemistry or materials science. Researchers are actively using early quantum computers and quantum simulators to study the behavior of complex molecules relevant to drug development, where the underlying quantum mechanical interactions between electrons are notoriously difficult for classical computers to calculate accurately once a molecule grows, even moderately large. Similar techniques are being applied to the search for new superconducting materials, new battery chemistries, and new catalysts for industrial chemical reactions, all of which depend, at a fundamental level, on quantum mechanical effects that classical simulation methods struggle to capture with full accuracy. In these more applied areas, researchers typically have the advantage of being able to compare a quantum simulation's predictions against real, measurable, experimental data from an actual physical sample of the material or molecule in question, which provides exactly the kind of independent check that is much harder to come by when the subject under study is a hypothetical wormhole or the long-term fate of the entire universe. This distinction matters for understanding why the verification problem hit the wormhole and false vacuum experiments so much harder than it hits many other areas of quantum simulation research. Both experiments were, by design, exploring physics that has no directly accessible classical or experimental point of comparison. Nobody has ever observed an actual traversable wormhole, and nobody has ever observed an actual bubble of true vacuum nucleating anywhere in the universe. The entire scientific value of both experiments rests on trusting that the small, simplified quantum system on the chip genuinely reproduces the relevant features of the much larger, inaccessible physical phenomenon it is meant to stand in for. And that trust is precisely what came under such close and, in the wormhole case, ultimately damaging scrutiny. Looking forward, several concrete lines of research are already underway that will likely shape how this entire story continues to develop over the next several years. On the false vacuum decay side, the Leeds, an Institute of Science and Technology, Austria, collaboration has indicated that extending their experiment from one spatial dimension to two, and eventually to a full three-dimensional simulation, is a realistic goal on existing or near-term quantum annealing hardware, assuming continued improvements in qubit count and connectivity between qubits. A genuinely three-dimensional false vacuum decay simulation would represent a substantially closer analog to how the process might actually unfold in our real universe, assuming the underlying metastability picture suggested by the Higgs, boson and top quark mass measurements turns out to be correct. On the quantum gravity and holography side, researchers are actively exploring larger and more carefully verified versions of the SYK model experiment, incorporating exactly the kind of provable fidelity guarantees that the field, in the aftermath of the Berkeley critique, now widely agrees should have accompanied the original 2022 experiment from the very beginning. Some groups are exploring entirely different, non-sparsified approaches to fitting a more complete version of the SYK model onto near-term quantum hardware, aiming to avoid the specific mathematical pitfall, the fully commuting Hamiltonian, that undermines so much of the original wormhole claim. Others are exploring whether Traptian quantum computers, a different hardware platform than either Sycamore's superconducting circuits or D-Wave's and might offer a more favorable combination of qubit connectivity and low error rates for running larger, more faithful versions of these holographic models. Meanwhile, the broader quantum computing industry continues pushing toward larger, more reliable, more fully error-corrected machines. Google, IBM, and a number of other companies and research consortiums around the world have each published multi-year roadmaps aiming toward quantum processors, containing many thousands, and eventually potentially millions, of physical qubits, organized using sophisticated error correction schemes into a much smaller number of highly reliable, logical qubits capable of running long, complex calculations without being overwhelmed by noise. If and when that kind of hardware becomes available, many of the specific technical limitations that forced the 2022 Wormhole team to shrink their model down so aggressively in the first place, the exact shrinking process that ultimately introduced the fatal, fully commuting mathematical structure, may simply cease to be necessary, allowing future experiments to run much more complete, much more faithful versions of these gravitational models, without needing to compromise nearly as much. It is worth taking a slower look at where the very idea of a wormhole comes from in the first place. Since the concept predates quantum computing by roughly 9 decades, in 1935, Albert Einstein and Nathan Rosen, working through the mathematics of general relativity, discovered that the equations describing a black hole actually permit a second kind of solution, one in which two separate regions of space-time, potentially very far apart, or even existing in entirely separate universes, are connected through a kind of geometric bridge. This structure became known as the Einstein-Rosen bridge, and it is the direct mathematical ancestor of what popular science writing later began calling a wormhole. For decades after Einstein and Rosen's original paper, this solution was treated mostly as a mathematical curiosity, since the simplest version of it is not actually true. Anything attempting to cross through it would be crushed, or the throat of the bridge would pinch closed and seal shut before anything could complete the crossing, making it entirely useless as any kind of practical shortcut through space. That changed, at least theoretically, in 1980, when the physicists Michael Morris and Kip Thorne published a paper working out the specific conditions under which a wormhole could, in principle, be held open long enough for something to actually pass through it safely. Their key finding was that doing so requires a form of matter with negative energy density, and substance that violates what physicists call the classical energy conditions, meaning ordinary matter of the kind that makes up stars. Planets, or people, simply cannot do the job. Such negative energy density is not purely science fiction, however. It does have at least one well-established real-world analog, called the Casimir effect, first predicted by the Dutch physicist Hendrik Casimir in 1948 and later confirmed experimentally, in which two closely spaced, uncharged parallel metal plates experience a measurable attractive force due to quantum fluctuations of the vacuum between them, an effect that can be interpreted as arising from a region of negative energy density created in the gap between the plates. The Casimir effect, though, produces only an extraordinarily tiny amount of negative energy, nowhere close to what would be required to prop open an actual macroscopic wormhole large enough for anything larger than a subatomic particle to pass through, which is one of several reasons wormholes of the kind imagined in science fiction remain firmly in the realm of theoretical speculation rather than engineering possibility. This is precisely the theoretical gap that the traversable wormhole protocol developed by Jafiris Gao and Wall was designed to sidestep, at least within the artificial, holographic setting of the SYK model. Rather than needing to physically manufacture negative energy density directly, the way an actual macroscopic wormhole would require, their protocol showed that a specific, carefully engineered quantum coupling between two entangled systems could produce an effect on the gravitational side of the holographic correspondence that behaves exactly like the negative energy pulse Morris and Thorne had originally required. This is part of what made the theoretical proposal so appealing to test experimentally in the first place. It offered a route to studying the physics of traversable wormholes without needing anything remotely resembling actual exotic negative energy matter, since the negative energy in question exists only on the gravitational side of a mathematical duality, with its physical origin on the laboratory side, being nothing more exotic than a precisely timed sequence of quantum logic gates. The broader concept of quantum teleportation itself, separate from any of its later applications to gravitational physics, has its own well-established history within quantum information science. The core protocol was worked out theoretically in a 1993 paper by 6 physicists: Charles Bennett, Gilly Brassard, Claude Crepeau, Richard Joser, Asher Pears, and William Wood, who showed that it is possible to transfer the complete quantum state of one particle onto a second, distant particle, provided the two particles share a prior entangled connection and a small amount of ordinary classical information is also communicated between them. Though this method destroys the original state as a fundamental consequence of the quantum no-cloning theorem, meaning the process should more accurately be understood as moving a quantum state rather than duplicating one. The first experimental demonstrations of quantum teleportation followed within just a few years. In 1997, carried out independently by a team led by Anton Zeilinger in Austria and a separate team led by Francesco De Martini in Italy, both using individual photons of light rather than superconducting qubits. It is worth being clear that this ordinary form of quantum teleportation, well established and completely uncontroversial by this point, is not by itself evidence of anything gravitational. The Sycamore wormhole experiment relied on this same basic teleportation mechanism as its experimental backbone, but the controversy was never about whether teleportation itself had occurred. It clearly had. The controversy was entirely about the far more ambitious additional claim layered on top, that this particular teleportation event specifically reflected the physics of a traversable wormhole rather than simply being an ordinary instance of a well-understood quantum information protocol running on a cleverly constructed circuit. There is also a broader lesson embedded in this story about the relationship between scientific research and the way that research eventually reaches the public, one that is worth sitting with for a moment. The original 2022 paper itself, read carefully by an expert, was reasonably careful in its technical language, framing its conclusions in terms of consistency with a set of expected gravitational signatures rather than making an unqualified claim to have definitively built a wormhole. But careful technical hedging of that kind rarely survives the translation into a press release, and it survives even less of the translation into a news headline. Caltech's own press materials described the result in considerably more definitive terms than the underlying paper itself did, and by the time the story had passed through several additional layers of media coverage, much of the original nuance had been smoothed away entirely, leaving behind headlines that described scientists as having built an actual wormhole, full stop, with little indication that this represented one contested interpretation of a small, carefully engineered laboratory signal rather than a settled scientific fact. This pattern is not unique to this particular experiment, and physicists who have watched it play out over their careers tend to recognize it immediately. A nuanced, carefully qualified technical claim enters the public conversation, loses its qualifications somewhere along the way, and by the time the story reaches its widest audience, it has often hardened into something considerably more definite and dramatic than the scientists who did the original work ever actually claimed. The subsequent correction, when it eventually arrives, as it did with the Berkeley critique and the later formal Nature Matters arising publication, almost never receives anywhere near the same level of public attention as the original announcement did, which is part of why so many people who heard about the wormhole experiment back in 2022 may never have heard that its central gravitational interpretation was later substantially walked back, stepping back even further. It helps to understand why physicists care so much about holography as a general framework in the first place. Beyond its use in any single headline-grabbing experiment, one of the longest-standing, most stubborn problems in all of theoretical physics is the difficulty of reconciling general relativity, Einstein's theory of gravity, which describes space-time as smooth and continuous, with quantum mechanics, which describes matter and energy in terms of discrete, probabilistic, often deeply counterintuitive behavior at very small scales. The two frameworks work extraordinarily well within their own separate domains. General relativity governing the large-scale structure of the universe, quantum mechanics governing the behavior of atoms and subatomic particles, but combining them into a single, unified theory of quantum gravity, one that can describe, for instance, what actually happens at the very center of a black hole, or in the earliest fractions of a second after the beginning of the universe, has proven to be an extraordinarily difficult theoretical challenge, one that has occupied some of the most capable theoretical physicists of the past century without yet producing a fully agreed-upon answer. String theory emerged, beginning in the 1960s and developing considerably through the 1970s, 80s, and 90s, as one of the leading candidate frameworks for eventually achieving that unification, built on the idea that the fundamental constituents of nature are not point-like particles at all, but tiny, vibrating, one-dimensional strings, with different vibrational patterns corresponding to different particles, including, crucially, a vibrational pattern that behaves exactly like the graviton, the hypothetical particle believed to carry the force of gravity in a fully quantum description. Juan Maldaceno's 1997 discovery of the holographic correspondence emerged directly out of string theory research, and it is widely regarded as one of the most significant theoretical results to come out of the string theory program in its entire history, precisely because it provided, for the first time, a rigorous mathematical example in which a full quantum theory of gravity could be shown to be exactly equivalent to an ordinary, comparatively well understood, quantum theory without gravity at all, existing in one fewer spatial dimension. This gave theoretical physicists an entirely new, and in many ways much more tractable, way of studying quantum gravity, by translating hard gravitational questions into equivalent questions about ordinary quantum systems, questions that could sometimes be tackled using existing, well-developed mathematical tools from particle physics and condensed matter theory. It is this exact translation, gravitational questions restated as ordinary quantum questions, that made the Sycamore experiment conceivable at all. Nobody was proposing to build an actual black hole or an actual wormhole in a laboratory, which would require completely unrealistic amounts of energy and mass concentrated into an impossibly small space. Instead, the entire strategy rested on holography's promise that a sufficiently well-chosen quantum system, one exhibiting the right kind of chaotic, fast-scrambling behavior, would be mathematically equivalent to a gravitational system, meaning that studying the quantum system directly would be equivalent, in a precise sense, to studying gravity itself. The controversy that followed was never a challenge to holography as a broad theoretical framework, which remains one of the best supported ideas in modern theoretical physics, resting on decades of accumulated mathematical evidence from many independent directions, including the entanglement entropy calculations of Rue and Takayanagi and the black hole, information calculations involving replica wormholes discussed earlier. The controversy was specifically about whether one particular, heavily simplified, machine-learned approximation to one particular model was still close enough to the real thing to count as a faithful test of that broader framework, which turned out, on careful examination, to be a considerably harder question to answer affirmatively than the original team had initially believed. This distinction matters enormously for understanding how to think about the whole episode. It would be a mistake to walk away from this story concluding that quantum gravity research in general is somehow unreliable, or that holography itself is now in doubt. The actual lesson is narrower, and in some ways more useful. It demonstrates, with unusual clarity, exactly how difficult it is to bridge the gap between an elegant piece of pure mathematics and a genuinely faithful experimental test of that mathematics, especially when the available hardware forces you to shrink your model down dramatically before you can run it at all. That gap between theory and a faithful experimental proxy for that theory is where essentially all of the difficulty in this entire story actually lives. And it is a gap that experimentalists working in quantum simulation are now having to grapple with far more carefully and explicitly than they generally needed to in the past. precisely because the theoretical territory they are exploring has become so much more ambitious. The scientific correction process itself, the sequence of events running from the original 2022 publication through the Barclay team's 2023 archive paper, through several years of ongoing technical debate, and finally to the formal 2025 Matters Arising publication in Nature, is also worth appreciating on its own terms, separate from the specific physics involved. It represents science working roughly the way it is supposed to work, even though the process was slower, messier, and considerably more public than most people might imagine scientific self-correction typically looks like from the outside. Peer review, the process by which other qualified experts examine a paper before it is published, catches a great many errors before they ever reach print, but it is not infallible, and it was never designed to catch every possible subtle flaw in a highly technical, novel piece of experimental physics, particularly one combining unusual elements like machine learning-driven model simplification with a genuinely unprecedented experimental interpretation. What caught this particular problem was not the original review process, but the ordinary, ongoing scrutiny of the wider scientific community after publication. Exactly the kind of scrutiny science relies on as a second, slower, but ultimately more thorough layer of quality control. The fact that Nature was willing to publish a formal critique of its own previously published high-profile paper, rather than simply letting the disagreement remain buried in less visible archive papers indefinitely, is itself a meaningful, if quiet, marker of the scientific process functioning as intended, even years after the fact. So where does all of this actually leave things? As of the middle of 2026, a great deal remains genuinely unresolved, and it is worth being honest and specific about exactly what is still unknown. Rather than reaching for a tidy conclusion the science does not yet support, physicists still do not know with any real confidence whether the specific sparsified SYK model used in the Sycamore experiment retains any meaningful gravitational content at all, or whether Pingal's proposed middle category, something he called pseudo-holographic behavior, will eventually harden into a well-defined, useful theoretical concept in its own right, or whether it will instead turn out to be a somewhat awkward label for a system that simply falls short of being gravitational in any rigorous sense. The formal exchange published in Nature in July of 2025 did not fully settle this question. It formalized the disagreement and clarified precisely which claims survive scrutiny and which do not. But a definitive, universally agreed resolution has not yet emerged, and may not emerge until considerably larger, less aggressively simplified quantum systems become experimentally accessible. On the false vacuum side, the central open question is considerably more concrete, though no less difficult. Extending the Jülich experiment from one spatial dimension into two, and eventually into a fully three-dimensional simulation, will require substantially more qubits arranged with considerably richer patterns of connectivity between them than current annealing hardware comfortably provides, along with improved methods for maintaining coherence across a larger, more complex system for long enough to observe genuinely three-dimensional bubble dynamics play out. Researchers in this area generally describe this as an engineering and scaling challenge more than a conceptual one, since the underlying quantum Ising model and its connection to false vacuum decay is already well understood theoretically. But engineering and scaling challenges in quantum hardware have historically taken years, sometimes many years, to resolve, and there is no strong reason to expect this particular case to move noticeably faster than similar hardware scaling efforts have moved in the past. There is also the broader harder question sitting underneath both specific experiments, the verification problem itself, and it remains very much unsolved as a general matter. The specific techniques researchers currently use, cross-entropy benchmarking, shadow tomography, randomized benchmarking, and the kind of careful theoretical reanalysis the Berkeley group applied to the wormhole experiment, are all useful, but none of them constitutes a complete, general-purpose solution capable of certifying the correctness of an arbitrary quantum simulation running on an arbitrary piece of hardware. Developing that kind of general verification framework, one that would let physicists trust the output of a quantum simulation, exploring genuinely unknown territory with the same confidence they currently place in results from telescopes or particle accelerators, is likely to remain one of the central open technical problems in quantum computing for years to come. And it is a problem that touches far more than just quantum gravity research, extending into essentially every serious application of near-term quantum hardware, from chemistry to materials, science to cryptography. None of this uncertainty makes the underlying research any less worth pursuing, and it is worth closing on why that is the case, rather than on the specific list of unresolved questions themselves. The fact that physicists can now build small, imperfect, sometimes misleading, but genuinely physical laboratory systems designed to probe questions as abstract and previously untestable as whether space-time emerges from quantum entanglement, or whether the vacuum of our universe is truly stable, represents an extraordinary expansion of what experimental physics is even capable of attempting. A generation ago, questions like these lived entirely within the realm of pure theory, explored through mathematics and thought experiments alone, with no meaningful prospect of ever being tested directly in a laboratory setting within any physicist's working lifetime. That situation has now changed, however imperfectly and however many false starts and necessary corrections come along with it. The wormhole controversy, in particular, has already left a lasting, constructive mark on how the field approaches this kind of research going forward. Researchers planning future quantum simulation experiments in this general area are now considerably more careful from the outset about distinguishing between a system that is rigorously mathematically dual to a gravitational description and a system that merely borrows some of gravity's mathematical language or produces superficially similar-looking data. Grant proposals, paper drafts, and conference talks in this corner of physics now routinely include exactly the kind of careful hedging and explicit acknowledgement of simplification artifacts that, in hindsight, many researchers wish had been more prominent in the original 2022 announcement. That is a genuine, lasting improvement to how this area of science is conducted, even though it arrived only after a fairly public and, for some of the researchers involved, undoubtedly uncomfortable process of correction. There is also something worth appreciating in the sheer scientific ambition connecting both of these experiments, contested and uncontested alike. A team of physicists looked at one of the strangest, most abstract conjectures in modern theoretical physics, the idea that entanglement and geometry might be two different descriptions of the exact same underlying phenomenon, and asked whether any piece of that idea could be tested using real hardware sitting in a laboratory in Santa Barbara. A separate team looked at a genuinely unsettling open question about the long-term stability of the vacuum we live inside, a question with roots stretching back to calculations from the late 1970s, and asked whether any piece of that mechanism could be watched directly, using a very different piece of quantum hardware sitting in Germany. Both experiments, whatever their ultimate scientific fate turns out to be, represent physicists reaching for genuinely new territory rather than staying safely within the boundaries of what earlier generations of instruments could already access. Somewhere in Santa Barbara, that dilution refrigerator is presumably still humming quietly along, its 9 qubits sitting at a temperature colder than most of the rest of the observable universe, waiting for the next experiment to be loaded onto them. Somewhere in Germany, a very different piece of hardware, built around a very different physical principle, continues to be refined and scaled up, with plans already underway to push its false vacuum simulation into additional spatial dimensions. Around the world, other groups are exploring alternative hardware platforms, developing better verification techniques, and working through the theoretical subtleties that the wormhole controversy brought so clearly into focus, each contributing, in their own way, to a slow, careful, occasionally uncomfortable process of learning exactly how far quantum simulation can genuinely take physicists toward answering some of the deepest open questions about the nature of reality. It is unlikely that any single future experiment running on any particular chip will resolve these questions all at once. In some dramatic, headline-generating breakthrough, that has never really been how this kind of foundational physics tends to progress. Progress here looks more like what has already happened over the past several years. An ambitious claim, careful, independent scrutiny, a partial correction, a clarified understanding of exactly what was and was not demonstrated, and then a slightly better designed experiment built on everything learned along the way. Whether the specific wormhole protocol pioneered by Gao and Wall eventually finds a home on genuinely larger, better verified quantum hardware, free of the fully commuting mathematical trap that undid its first attempt, and whether the false vacuum decay experiment eventually grows into a fully three-dimensional simulation capable of speaking more directly to the actual fate of our own universe, remain open questions that only time and a great deal of careful, patient, occasionally frustrating, experimental and theoretical work will be able to answer. For now, what exists is a quiet, ongoing conversation between two of the deepest frameworks in modern physics, quantum mechanics and gravity, conducted using some of the strangest, most delicate machines humans have ever built, chilled down near absolute zero, holding fragile quantum states together just long enough to ask questions that, until very recently, nobody imagined could be asked inside a laboratory at all. Some of the answers coming back are turning out to be real signals. Some are turning out to be artifacts, echoes produced by the very simplifications needed to make the experiment possible in the first place. Telling the difference between the two, reliably and with confidence, is exactly the quiet, patient, unglamorous work that theoretical and experimental physicists are now settling into for the years ahead. And it is, in its own understated way, one of the more genuinely interesting places in all of contemporary science to be watching closely, even as it remains, for the moment, comfortably and honestly unresolved.